Yes, success. Okay, so we are recording, so we have an archival copy. And with that, let me hand the meeting over to Group 13 to present their design project for us.
Hello, everyone. So as Dr. Trom mentioned, we are Group 13, Activate Reactors to Next Generation in Bioreactors. The engineers involved on this project were myself, Jonathan.
Myself, Michael DeLuca.
Andrei Grubisic.
Sarah Grisman.
Luke Jacob.
Connor Lysick.
Sharif.
So just to briefly go over the agenda for the presentation today, we'll first discuss the hedgehog concept, then we'll go into a product overview, the overall design, and then we'll break down the design into the subsystems. We'll highlight some key design features, go over the cost overview, and lastly, why activate.
So a challenge for our team was determining how to stand out against competing designs with a concept that mirrored our values. So with continued concept generation and design, we found that we were interested in making a design that was efficient in terms of function and user friendliness, especially when it came to complex bioengineering technologies such as bioreactors. So Activate Bioreactor seeks to provide a competing solution to autonomous bioreactors in this field.
So today we will be discussing our design for a semi-autonomous bioreactor. The device's user interface allows the user to adjust settings like heating and cooling, the number of tubes to incubate, and varying vibration patterns. The heating elements are located on the bottom of the incubation chamber, while the refrigerating coils are placed near the top. Since warm air rises and cold air falls, this design encourages natural convection. A gas mixture from the tank located on the right-hand side of the design will be injected into the main enclosure to culture the specimens. But before this happens, an exhaust turbine takes out ambient air in order to get a controlled atmosphere inside the reactor. Since we're injecting possibly a large amount of gas into our sealed volume, we've installed a check valve which can mechanically regulate the maximum pressure inside. Our accurate stepper motors of the fluid transport system, which control the X and Y position of this dispensing tips, can move in increments of 0.007 degrees. Movement of the liquid handling system, on the other hand, is in the Z direction and is controlled by a linear actuator, which hangs from the gantry-style fluid transport system. Here we can get an idea of the scale of our design. It has a height of 47.6 inches, a length of 55.12 inches, and a width of 31.5 inches. Now we'll go into the specifics of each of our subsystems.
Starting off with our prototype design for the user interface system. As you can see from the isometric soliders view in the figure on the right, the UI system is part of the housing, which consists of a tablet, button and control switches, LED light, and an emergency shutoff switch. The tablet will be pre-programmed to the motherboard, which would control and connect users' actions from the display screen. The tablet would contain an automated rest mode feature in case of an emergency, such as a culture condition malfunction. This will indeed satisfy customer needs 6, 13, and 14. In the case of this emergency or any other, the system would enter automated safe rest mode, and the actions will stop until the emergency shutoff switch is either pulled by the user to continue the actions or pushed by the user to completely shut off the reactor's actions. This satisfies customer need number 7. The LED light will serve as a purpose of a visual indication whether the function is being successfully performed. It will light green, or if the functions have stopped, it will blink red. This would satisfy customer need number 9. Now, button and control switches located above the tablet would be used to navigate and control functions performed by the user on the reactor. Lastly, in order to assess the technological maturity of our design, we use the technological readiness level scale of 9 possible levels. When it comes to the technology readiness level, although our UI subsystem contains certain OTS parts which were lab tested, flight proven, and would alone receive the high score of TRL 9. However, in the combination with other functions and parts of this subsystem, it would receive a TRL3 since those parts and functions were never lab tested or put to operational use, at least not yet.
The liquid handling subsystem is vital to the design to accurately and quickly move fluid throughout the bioreactor. A linear actuator on the liquid handling subsystem connects to 8020, which is mounted to the fluid transport system, which we'll see later. The linear actuator allows the dispensing tip to have z-axis mobility and complete the three-dimensional capabilities of the transport system. Actuators allow the dispensing tips to extract and dispense from any point within the bioreactor to fulfill various customer needs in relation to the fluid dispensing. Pressure change drives a piston and allows the tips to dispense in 1 microliter increments with an accuracy of plus or minus 1 microliter and a precision within 2%. The 3-tip design is unique to the Activate bioreactor and an important feature in the overall design. This allows for increased speed when dispensing and extracting fluid. The 3-tip design also aids in the prevention of cross-contamination throughout the bioreactor. And the cleansing of these tips happens by dipping the tips in a viable cleansing solution within the bioreactor and extracting the solution throughout the tips. The subsystem would then disperse said fluid into waste containment area, which was within the bioreactor. And if one tip were being used to dispense fluid and in a quick fashion, another tip needed to be used to dispense a different fluid before the cleansing process, the 3-tip design is a unique feature to allow this function without cross-contamination. The subsystem was placed in TRL3 because its various components are flight proven. However, further prototyping and testing would be needed to move it up the readiness levels. In order to ensure the fluid dispensing subsystem maintains accurate and precise dispersion, the fluid motion was analyzed using Rayleigh Number. For this calculation, the minimum customer requirement of 225 microliters per second was used as the flow rate. Without direct knowledge of the various fluids to be tested using the bioreactor, water was deemed a viable replacement for these calculations. Thus, we performed the calculations with density and viscosity of water at 35 degrees Celsius, which is about the median temperature range of the incubation. The Rayleigh number is found to be well under the 2300 threshold for laminar flow, thus ensuring flow would not be turbulent and maintaining accurate results. The dispensing force was also analyzed for the fluid dispensing subsystem using a modified Bernoulli's equation where pressure at the outlet and movement in the barrel section were neglected. The volumetric flow rate was once again used at 225 microliters per second, and after substitution of the various parameters and working out the equation, the force required was found to be a very small 0.7 millinewtons.
The fluid transport subsystem's main purpose was to provide mobility to the liquid handling subsystem, which allows the user to perform pre-programmed functions with input with the user interface subsystem. The method of movement that we ultimately chose was a rack and pinion system, which is reliable mechanically and performs the task necessary. We also decided to use a 8020 aluminum frame, which is strong enough to withstand any forces present during the typical processes and is easy to assemble. The motors that we selected are capable of programmable control and automated processes, which covers customer needs 13 and 25. And the use of limit switches prevents the overall system from becoming lost. For instance, if the system is powered down and the motors are just at some point in space, the system doesn't know where the origin is, our predetermined point of 0, 0. So these limit switches give the system, I guess, some vision, which allow it to find that origin again once the system is powered back on. Once again, although the motors and other features have been tested and flight proven and would be considered TRL level 9, the overall assembly has not been proven anything past just analytically and through calculations, so it's just a TRL level 3. Speaking of the calculations, the maximum linear speed was relevant in this case, and overall using the motor specs, and it turns out I believe 900 RPMs, which is quite quick. The maximum linear speed is 29 feet per second, which again is very quick. But ultimately, we decided this was necessary as we did not want the overall efficiency of the system to be bottlenecked by this particular subsystem. So we wouldn't actually ever operate at 29 feet per second, but it won't be the cause of a slowdown. This speed does correspond to both the X and Y directions, as the gear train and motor configurations are the same in both directions.
Moving to the vibration subsystem. The vibration subsystem consists of two linear actuators that are attached to a steel tray which holds the stands containing the incubation media. The two linear actuators are connected by ball joints that allow the actuator to produce all the shaking patterns that were specified in the customer need 31, the linear orbital and double orbital shaking patterns. The used actuators are 30 IPM SPAL linear actuators. These actuators will be supplied by a power source of 12 DC voltage. The speed of each one is half an inch per second with no applied load, and the static load of each one is 500 pounds with a stroke of 2 inches. There are 4 bronze wheels attached to the bottom of each tray to prevent the load being applied to the actuator. The reason for using bronze as the material is because the coefficient of static friction between bronze and steel is relatively low. It's around 0.2. In addition, a light source will be installed at the top part of the tray that will be projected at the conical tubes and the culturing plates containing the fluid. The positioning of the light will be addressed later on in this presentation. And then if we talk about the TRL, although most parts of the vibration subsystem are OTS and flight proven, meaning that they would achieve a TRL level of 9, but however, since the overall subsystem design has not been prototyped for its particular purpose, the TRL will receive a TRL of 3. And then moving to the incubation subsystem, it consists of a combination of conical tubes and culture plates. The system accompanies for all the sizes that were specified in customer needs 22 and 23. The design contained both the sizes specified for the conical tubes, the 15 ml and the 50 ml. And it contains, and all the sizes specified for the culturing plates that ranges from 60 to 384. The incubation media will be held still in different stands, where each stand was designed to hold the tubes and plates steadily and secure them in their position while the actuator are vibrating the whole system. The stands are made of acrylic in order to let the light pass through it and then through the incubation media for the FI and OD readings. Also, this design received a TRL 3 because of the same reasoning as for the vibration system, as it's not prototype for this particular purpose yet, even though like it was the tubes and culture plate were used in like laboratory before.
So another of the incubation subsystem includes the heating and cooling of our overall incubation. And so the heating and cooling system is able to achieve a temperature range from 4 degrees Celsius to 70 degrees Celsius, and it's modeled after the vapor compression refrigeration cycle. So this satisfies customer need number 20. And so to just go over the heating and cooling elements that we've included in our design, when the gas is introduced into the system, they pass these preheating elements shown in the top right. And so this would be a bottom view of the overall design. And so the preheating elements would allow the gas to be heated before passing into the main incubation chamber. And the reason we included these preheating elements is to improve the efficiency. And so after doing some very simplified calculations, in order to fill the entire incubation chamber with preheated gas, it would take a little bit over 3 minutes. And then to maintain the temperature, we would use the heating elements shown at the base in the bottom right. And so the reason for these heating elements is to counteract any thermal leakage that's occurring through the walls. We calculated that there'd be about 670 watts of thermal leakage through the walls. And so these heating elements are primarily to counter that. And then we also calculated a Rayleigh number on the order of 3 to the 11th, 3 times 10 to the 11th power. And so typical Rayleigh numbers the cutoff point would be at around 1 × 10 to the 9. And so below that value, the flow regime is described as laminar, and above that value, it's described as turbulent. And so based on this Rayleigh number, we can say that we predict a turbulent flow regime inside of our main incubation chamber. And so this might be observed via spiraling of hot air upwards, and then the cool air at the top would come down. And so this convection was designed intentionally by placing the heating elements towards the bottom of the design and the cooling elements towards the top of the design. And so for cooling, we have the condensing unit, which is located above the reactor. And then we also have these refrigeration coils towards the top of the reactor. And so again, this bottom left image is a view from the bottom of the reactor. So if you're looking through the base towards the top, this is where the refrigeration coils are located. And so with these refrigeration coils, we're able to remove about 700 watts of heat from the system. And then using some specific heat calculation, we determined that the time to cool the subsystem would be around 2 minutes. But this is a very simplified calculation, just based purely on the power of the condensing unit, and it ignores a lot of other aspects that could be relevant in the actual design. And so for that reason, again, that's why this incubation subsystem would receive a TRL level of 3, because it actually hasn't been tested and it's only been analyzed analytically. For the fluid monitoring subsystem, we met customer needs number 20 and number 29, which described being able to measure OD and FI. We completed this using a TCS 3200 sensor, which uses filters to measure fluorescent intensity, and it can measure wavelength and light intensity. And for our system, the light intensity that was needed was achieved via high-powered LEDs. The high-powered LEDs can provide 1 kilowatt per centimeter squared of light intensity at the specified wavelength of 640 nanometers by customer need number 30. And so these low wattage LEDs were able to achieve this high light intensity via the placement of the LEDs by placing them very, very close to the well plates, which are acrylic and see-through, shown in the bottom left. We're able to achieve a high light intensity at the samples, which are just above, like inside the well plate. And so since this is, again, not a flight-proven completed subsystem, it received a TRL of 3 as well.
So for ease of control and around the system, we have a rack and pinion mechanism in the liquid transport system that allows for X and Y axis motion, which was shown above. And a linear actuator in the liquid handling system provides Z-axis motion for ease of control around the system. To go along with our desire for increased efficiency, which goes along with our hedgehog concept, a predetermined gas is attached to the system by the user and preheated by 2 heating elements before entering the incubation area, which allow for faster heating of the environment. Also, to account for addition of gases into the system, which increases the pressure, and for the removal of effluent gases, which is a customer need, an exhaust fan and check valve ensure proper and safe removal of these fluids from the system. And the check valve is a safety measure for when the pressure becomes too large. It's a redundant feature in case the exhaust fan fails to exhaust gas and reduce pressure.
And here we have the cost overview of the Activate Bioreactor project with the customer need of staying within budget of $10,000 in mind. The off-the-shelf cost of $6,265 was the largest portion of the cost, with items such as the condensing unit, motors, drivers, controllers, and the user interface system taking up the majority of that cost. Modified off-the-shelf parts and raw materials were $414 and $316 respectively. And manufacturing labor was around $1,000, due mainly to the casting, welding, and the use of CNC in this design. Energy consumption for the city of Gainesville was researched and found to be about 10 cents per kilowatt hour, which comes into play with the condensing unit and the heating elements within the system. And finally, the cost of assembly labor was about $214 and was established using the Boothroyd and Dewhurst assembly time charts. And the total cost of the project came out to about $9,263.31.
In conclusion, our preheating and triaxial control supports an effective and aesthetically pleasing design. Our overall design is cost effective and it satisfies all the customer needs. Coming into this project, we're all mechanical students, and being giving a biomedical project was a huge challenge. So a lot of the background research, I mean, we came into this project with no biomedical experience and no biomedical knowledge. So we actually enjoyed learning what a microbioreactor is, and how it's supposed to function. We learned more concepts and were able to apply the concepts that we had learned previously through school. And we are proud of our design and firmly believes it deserves to be prototyped.
Group 13 would like to sincerely thank EML4501 faculty, teaching staff, and sponsors for their continued support. Any questions are welcome at this time. We would love to hear your feedback.
I've got a few. And Dr. Trump's laughing now when I say that. So first off, I just want to make a statement here. This wasn't a biomedical project. This was a mechanical engineering project, as you guys discovered. It was just framed around solving a problem in biology, because biologists are good at growing things. They're not good at solving heat transfer mechanical systems. So I'm making that statement here, like, yes, there was biology, and I'm really happy that you guys learned a bit, but this is a mechanical engineering project through and through for you guys. So guys, back when you were talking your fluid flow stuff, somebody mentioned Rayleigh number.
Yes.
Rayleigh number for getting turbulent flow. Is that the correct non-dimensional number?
No. Well, so for turbulent flow, you'd be using Reynolds number, but based on what I was finding online for Rayleigh number, it was describing turbulence of like the air as its convective. And so that's why I put that turbulent there. So I was able to find like laminar regimes and turbulent regimes. And so that's why I put that there.
Okay. I've never seen Rayleigh number for turbulent flow before, so I was a little bit confused.
More so describing like the spiraling effects that would occur and other like turbulent like phenomena that would be observed in the heat transfer as the hot air is rising and the cool air is falling.
Okay.
Yeah, sorry if that was a little bit unclear.
Yeah, it was just like Reynolds number is always the thing that I've seen as being a descriptor for laminar and turbulent flow. Rayleigh number would come in, like you just said there at the end. It's a buoyancy number, I believe. Am I correct there?
Yes, it
Matt,
is.
You're the fluids guy. Rayleigh's a buoyancy. It's intermixing fluids with different densities.
Rayleigh number has a bunch of different purposes, and one of them is actually for natural convection to determine whether the flow structure is laminar or turbulent. So they're not wrong in doing it that way. Okay, cool. I'm not a heat transfer guy, so I saw that and was like, what? You guys have a lot of 80-20. Why?
We thought it was effective in being both modular, easy to assemble, and allowing for easy attachment with the rack and pinion system. And then also, I mean, although it is a little bit expensive, we just found that it outweighed the cost of. We just thought it was easier to assemble. Honestly, that was a huge thing, and it was modular. It's easy. It's quick.
So once I have my assembly initially put together, like my frame structure that you guys have made entirely out of 8020, am I ever going to be disassembling it again for the purposes of modularity?
Most likely no.
All right, so then why 8020?
Fair point.
You know, you guys use 8020 because you see it in DML. And I was a DML TA for 6 years. So I know everything about it. I know why you guys picked it. Like, if something is going to be a permanent structure, don't make it out of something non-permanent. Even for the sake of modularity. If you want modularity, put everything on, you know, 1/4-20 tapped holes on 1-inch hole centers and drill a flat pattern plate that you can bolt things down to for modularity. But look at other laboratory equipment out there. I've never, besides something kludged together for an experimental lab, there's no commercial OTS products that use 8020 in them. You know, I build stuff out of 8020 in my lab. I'm sure that the engineers at Cummins and Northrop, when they're building something for a test lab, use 8020 to build something real quick. But if there's something that they're buying for a permanent installation, I doubt 8020 is being used extensively. And they can weigh in on this and prove me wrong if I am incorrect there. But so just one thing there's better options than 8020. You guys seem to love it and it irritates me. And then my last thing is, your final cost, you had 6K in OTS parts. What were the expensive bits there? Because I don't remember hearing exactly what the expensive bits were.
Okay, yeah, I can touch on that. So I know the condensing unit was very expensive. I think it was very close to $1,000. And then basically the motors, drivers, and then like the tablet and whole user interface system took up a majority of that cost.
What tablet were you guys using?
Windows 10 tablet.
Okay, that's why.
Yeah, we did some research on it. I know the initial thing was an iPad, but I know Windows is like the most compatible with a lot of the programming knowledge we have. So I figured Windows 10 was probably the best to go with.
I mean, if you use an iPad, it would have cost you like 4 times as much. So
exactly. Yeah, I think the Windows tablet was like $250.
Yeah,
around there.
Yeah, just how big are your motors?
Because like dimensionally, or is that what you're asking?
No, like what size motors? Like, so I'm assuming, are they like NEMA frame motors?
Yeah, it's 23 NEMA
23s. Yeah.
How did you? Okay, I'm thinking I'm doing the internal cost. I'm like, all right, cool. So you're at 5K once you get rid of the condenser unit, and then your motors, like, you know, how many motors are there that you guys are racking? The cost is kind of surprising me. Even so,
I can touch on it a little bit. There are 2 NEMA 23s which are on the fluid transport system, and the liquid handling subsystem has one large linear actuator, which was quite easily seen, and then there's actually 3 smaller linear actuators located on within each dispensing tip, which allow for individual motion there as well.
Okay.
And there's also controllers and things like that allow, you know, so the cost does add up.
Are your controllers, are you doing open loop or closed loop feedback control?
Closed loop.
Closed loop? Okay. That's where your cost is coming from then.
Yeah. It was the controllers that McMaster had were compatible with the 23.
Okay. Death by McMaster car. All right, I'll let the rest of the crew here ask questions. I've eaten up enough time.
Thank you for your questions.
Hey there, I have a question. How are you controlling the temperature inside the incubation chamber? I understand you have the cooling and heating units, but how are you actually, so I think you have a temperature range between 4 and 70 degrees C. So if you want to reach a 30 degrees C target temp, how are you controlling that?
So you got it, Jonathan.
Yeah, so that would be controlled by the amount of preheated gas that's injected in, or like the temperature that the preheated gas is injected in at. And then it would use the heating elements to maintain the temperature at whatever is set.
I also don't believe we touched on this, but there are multiple temperature sensors located throughout the design. I believe there's one on the liquid handling subsystem, and I believe there's also another out on the wall of the
the overall design that's kind of tucked in the corner. That will help us get temperature readings and then, know what to do with the heating elements.
Okay, yeah, that was one of my questions. I didn't see any of the sensors, so I was wondering how you were controlling with the feedback loop. So
Can you guys go back to like an overall image of your entire design so we can see that while we're poking holes at it?
Yeah, of course. Just think it's at the beginning.
thank you.
Do you guys think this one is good or the next one?
That's good.
I think this is a good one. I think Ryan has a question in the chat. He says, what type of gas is being used for the refrigeration cycle? I mean, I believe the intent was to, depending on what type of test was being done, that there would be a variety of gases that were being pumped into the system, predetermined by the laboratory assistants.
I think what he means is what's your refrigerant?
I think we're just recycling the
The condenser uses refrigerant R134 as its rate from the manufacturer. So that's what it was designed to be using.
All right. Why'd you guys go with a turbine style exhaust fan pump, besides trying to, really show off to Cummins?
I don't think you go ahead. I mean, I'll take it. I don't think there was any really specific reason as to why we chose a turbine pump other than it being just effective in removing the pressure from inside of the system. I don't know if there was any real driving force behind us choosing that specific exhaust pump.
Okay.
Hey, I have a question about your shaker.
All right.
I was wondering if is the middle or the sides captured? I'm having trouble visualizing if one axis is.
I think are you cutting out? No internet issues maybe?
Yeah, Daniel, we're not hearing everything you're saying.
Do you want to put your question in the chat maybe, and then we can grab it from there? So the vibration subsystem has two linear actuators, and they're each connected with ball joints, which allow a little bit of rotational motion. Okay, with the actuators not bent if the other axis is moving. So the bronze wheels here will prevent it from bending vertically, and the ball joints are allowing it to bend in the other directions diagonally. And we're trying to keep as much load off of the actuators as possible with those bronze wheels, and yeah.
So I think I'm drawing what Daniel's talking about here.
Okay.
He's basically asking one of the actuators.
If this actuator moves down,
yep,
wouldn't that cause some type of, this actuator here would now have to either bend or it would have to change in length. Regardless, so otherwise you're not going to be moving, you're just going to be rotating.
Yes, the idea was that they would be coordinated, so that one would change in length as the other one was moving down, or whichever configuration you're trying to achieve, and then there'd be ball joints at each connection.
The ball joints aren't honestly very well visualized here, but they do connect to the outside plate, and then which allows for that rotational motion. Were any wear calculations done to see if the bronze wheels will wear out during the lifetime of the product? The main reasoning behind the bronze wheels was due to the low coefficient of friction with the steel housing. I believe the coefficient of friction was 0.2, if I remember correctly. I don't think any wear calculations specifically were done, though. That is something we should definitely do in the future, and we'll most likely do for the FDR.
if you were concerned with low friction, why didn't you go with Teflon or ultra high molecular weight polyethylene or another low friction polymer? Teflon's got a coefficient of friction of 0.1. UHMW has one of like 0.15. You know, also, is this bronze solid bronze or is it oil impregnated bronze?
Michael, do you know that?
I wasn't really, I don't think we totally consider that, but I'd imagine the oil impregnated would be preferable. And I do think, yeah, maybe the Teflon is a good idea for the future.
Okay. So if you're going to have oil impregnated bronze, can you think of any issues with putting oil into a region with biological systems?
Yeah, there definitely could be some contamination issues. Yeah, I think that changing the material of those wheels might be something we're gonna definitely look into.
Take a look at it.
Yeah.
We have time for a few more questions because our designated end time is 11:30.
I guess, why'd you guys go with a rack and pinion instead of a like belt driven? So, because your rack and pinion is very, very reminiscent of a lot of the hobbyist and CNC routers and 3D printers, and gantry style 3D printers, but they all use belts and a belt drive of some sort instead of steel rack and pinion. So why rack and pinion here over another similar comparable drive system?
I think overall it was just the best choice, and the for us in terms of the concepts that we came up with and kind of what we were able to select from. We had, I think, even like some off the wall things like electromagnet driving systems and some crazy concepts that we came up with during CDR, and ultimately it came out to be the most cost effective and I guess mechanically reliable system that we were able to choose from.
I think also for a belt system, it could become a problem if the belts become detached or something like that, or if they're protruding past the edges, it becomes more difficult to enclose it within the incubation chamber. So the shape of the rack and pinion made it like a much more suitable design choice.
All right, cool.
Okay, any final questions from the panel for group 13? Nope. Okay. Well, then, hey, we get to end 1 minute early. That never happens. So, okay. So we'll wrap it up there. Seeing no more questions. So I want to thank you guys for sharing your design with us and giving us this presentation this morning. We'll wrap it there. For the panelists who are here, just a reminder, we've got another one that'll start in about a minute at 11:30. I've just dropped into the chat the link, the web link that takes you to the page that has the agenda with the Zoom link on it. So we'll click on group 1. Their team name is Abyss. They're running from 11:30 to 12:15. They've got a Zoom link there, and we'll reconvene there in about a minute. So with that, we'll thank Group 13 one more time and wrap up and move on to the next meeting.
Thank you, everyone.
Thanks, everybody.
Thank you, guys.
Thank you. Have a good day.
Have a good one.
Nice job, guys.
Thank you, Sammy.